When it comes to the functional form of regression models, we have a few choices. The first one is called the level choice, and level means that if you have a dependent variable, which let's say dependent variable is y, which stands for household spending on food, so let's call it food spending, and we have an explanatory variable, and let's say the food spending is in dollars, and we have an explanatory variable x, which is household income, which is also in dollars. Okay, so let's call this household income, and it's in dollars. Good. Now, when both income and household spending on food is in its own value, that is dollars, then beta 1, which is right here, gives you the impact of a unit change in income on food spending. It means that what would be the impact of a dollar difference in your income? If your income increases by $1, how much more will you be spending on food? Now think about it. Do you really want to know the difference in spending based on an increase of $1, right? That would have a negligible impact on food spending. What you really want to know is a percentage increase in income. What is the percentage? What is the impact of X percentage increase in income on food spending? And for that, I'll bring you to the fourth one, where you take the natural logarithm of both dependent and an explanatory variable. So y being the food spending, take the log of that, and then take the natural logarithm of income, and then when you compute the model, you get a coefficient which is beta 1, and this coefficient is basically elasticity. In fact, it is telling you what is the impact of a percentage change in income on a percentage change in food spending, and this estimated coefficient becomes elasticity directly. Right, and so if you get the coefficient as 0.2, it means that a percentage increase in income would have a 0.2 percentage increase in food spending. It could also be true that X, instead of representing income, represents a household size. Right, how many members of a household? 2, 3, 4, 5, 6. In that case, it makes sense to not log transform X, which is this case number 3 right here, right? Why? Because if you log transform X, then you say, oh, percentage increase in household size, but nobody's household size increases by 1 or 2%. It always is a discrete change in household size. If this is a household size of 4, then it can grow up to 5, or if it's a household of 1 person, it can become 2 and 3, and so on and so forth. And when you have the dependent variable log transform, that is spending on food, and the independent variable as in its own case, which is level, then the estimated coefficient beta 1, when you multiply it by 100, it gives you a percentage change in the explanatory variable. So basically, if the household size changes by 1, that is, if there's an additional household member coming in, or if there's any change, there's one less member in the household, you take the coefficient, multiply it by 100, and it tells you what that unit change in the explanatory variable will be in terms of percentage on food spending. So let me say this. Let's say our coefficient ends up being 0.02 or 0.2. Or 0.2 would be the coefficient. So let's say beta 1 ends out to be 0.2, and if I multiply it by 100, then it's 20%. It means that when a household size goes up by 1, so there's one more additional member in household, then the food spending goes up by 20%. So that is called the log level explanation. Sometimes the case may be that the dependent variable, which is y, is not log transformed, but the explanatory variable is, right? And in that case, you divide the coefficient by 100, and then it gives you the impact of unit change in the explanatory variable on the in terms of percentage on the dependent variable. And I've never used this form, which is number 2. Most common form used in economics and in most studies is this log or log level, and then also level as well, which is the 4th, not in terms of the way they are listed, but this is the most common form, this is the second most common form. This number 3 is this. Let me call this as number 2. This is the second most common form, then 3, and then 4. And so when you look at research, published research, you would see that often they talk about elasticity, and elasticity is nothing more than the fact that they have actually log transformed the variables beforehand, and then the coefficient is directly an estimate of the elasticity. I've been talking about the model fit and adjusted R-square or R-square. Let me just briefly explain what does it mean. R-square is a mean of it's a goodness of fit statistic, and it varies between 0 and 1. Often you will see it written as 0.45, which is the same as 45%, right? And an R-square of 0.42 or 42% suggests that the model is explaining 42% variance in the dependent variable. What it means is this model is explaining 42% of the dependent variable, or it has a fit of 42%. Now you may think ideally that your fit should be closer to 100%. Theoretically speaking, yes, but it seldom is the case, and that shouldn't be the driving force behind the choice of the model that you would present. The model should make intuitive sense rather than going after higher R-square. And you should know that aggregate data by default would have higher R-square. Compared to disaggregate data. So I give you an example. If you are looking at the individual or household level data, such as household spending on food, and you have, say, 500 or 1,000 or 2,000 households, your R-square would be low. It will be in the range of 20 to 50%. But it doesn't mean that this is any less accurate than aggregate data. There is something called the aggregation bias, which is common in aggregated data, and the aggregation bias is the reason why you get a higher R-square in aggregate data. So it is resulting from a bias rather than it's a good thing. So be very mindful that with the aggregate data you get an R-square of 50+%. And disaggregate data you get a lower R-square. The other thing is we've been discussing this thing called conditional mean, and I've been referring to it in the past, which is the intercept in a regression model. And so what does it mean? What does it mean to have this beta knot? Let me give you an example. We have the data on housing prices, but I have computed the average house price in dollars for a data set, and I have minimum number of bedrooms in our data set as 1 and the maximum number of bedrooms as 6. And you would notice that the average price of homes with 1 bedroom only was $38,750. For 2 bedrooms, average price was $51,886, and all the way to 6 bedrooms, the average price was $68,000. Now, what is conditional mean? Let's say I create 5 dummy or binary variables. So let's say if a house has 2 bedrooms, I call that variable 2 beds. And if the house has first house has 2 bedrooms, I say 1, and the next one has 3 bedrooms, so this variable would become 0. And as long as the number of bedrooms is 2, it's going to be 1, otherwise it's going to be coded as 0. Same goes for, say, 3 beds, and it could be 0, 1, 1, 0, 0, or 1 bedroom, which could be 0, 0, 0, 0, 1. Right. So, what does it mean? So each variable characterizes the house as a certain bedroom type, and I entered the these variables. With the exception of 1 bedroom, I entered the variable as 2 bedroom, which is a binary variable, 3 bedroom right here, 4 bedroom, 5 bedroom, and 6 bedrooms. And notice that the 1 bedroom is not entered. And what happens is when I run the regression model, I get the intercept and the coefficients. These are the betas. So the intercept is $38,750. This is by default the conditional mean, and because the other variables are the number of bedrooms 2, 3, 4, 5, 6, you could see that the beta naught is the conditional mean, and basically beta naught is the same 38,750 here, and which is captured as the intercept. So if conditional mean is that if all other explanatory variables assume a 0 value, then the conditional mean would be the value of the dependent variable. So here we had only other variables were capturing the size, number of bedrooms. If we substitute 0 for all of them, then the number of then the price of the property with 1 bedroom becomes 38,750, which is exactly what we have here. So that is the conditional mean. Let's say we have 2 bedroom home, so the coefficient is 13,136. If you add 38,750 and add 13,136 to it, that gives you the price of 2 bedroom from the model, which is 51,886, which is exactly the same here. Look, 51,886. And you could do the same. Add, let's say, 44,390 to 38,750, and you get $83,140 for 5 bedroom home, which is the average price of a 5 bedroom home. So this is the same as this. And the conditional mean basically is when all other variables take the value 0, what is the conditional mean in that case? And that is 38,750, which is the average price of a 1 bedroom apartment. Now the error term that I've referred to, which is epsilon, or written as this symbol, which is epsilon, epsilon or epsilon, it doesn't matter how you pronounce it. This tells us it's actually a difference between the observed value, I've written it somewhere, and the forecasted value. So you estimate a model, and then from that model you estimate the forecasted value, which we call y hat, which is the forecasted value, and then the difference between the forecasted value and the observed value, which is y, that difference, that is y minus y hat. Oh, it's not coming out well. Let me write it again. Y minus y hat is the residual, or the error term, and that is the difference between the forecasted and the observed value that we cannot model, and that we cannot account for.